Hey, it's Dr. J. We're finishing 2.5 today with prime factorization. In the last lecture, we talked about prime numbers. So just a quick reminder, recollection of what the prime number is, what a prime number is. A natural number, I'll spell it right. A natural number, or a counting number, is called prime if the only factors are itself, whatever itself is, and 1. Okay? In other words, it is only divisible, if you like to think about it in terms of divisibility, by itself in 1. We call that a prime number. This is intentional. Prime factorization is what we're going to be talking about today. Prime numbers are the numbers that are only divisible by themselves in 1. For example, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and I'm getting tired, so I'm just going to stop. The list goes on forever. There's an infinite number of primes. That is a story for another day. For today's lesson, you could probably get away with just knowing these primes. Rarely ever are we going to get much larger than that, unless we were to dedicate an entire semester to prime number theory, which is a whole nother story. Today, we're going to be talking about composite numbers. A natural number is called composite if it is not prime. So a number that is not prime, we call that a composite number. Okay. And then 1 is neither. So just to put that out there right away, 1 doesn't count. 1 is neither prime nor composite, so it's in a category of its own. It is neither prime nor composite. So the primes and the composites, they start with 2. Okay. The smallest composite number is 4. Yeah. Let's see, 4, and then maybe 8, 9, 10. So on and so forth. We're going to talk about much larger composite numbers. So that's kind of the setting that we're going to be working with today. What is a factorization? So we'll take a composite number. Our goal, to take a composite number, such as, I don't know, let's do 16. I don't want to start too big. So we'll take a composite number, and we want to factor it. Into only prime numbers. So I could take 16 and I could say 16 is 2 times 8. Yeah. And so this is called a factorization. This is a factorization, 2 times 8. I could say 16 is 4 times 4. Yeah. This is also a factorization. I could say it's a different factorization. Different than the previous factorization, but these are still both considered factorizations. But they are not prime factorizations. Since not all the factors are prime, they're not all prime. 8's not prime, 4's not prime. This is not called a prime factorization. To have a prime factorization, I'm writing it again. I know it's already up there. The prime factorization of 16, well, 2 times 2, that's 4, times 2, that's 8, times another 2. All of these are primes. So this is a prime factorization. 2 times 2 times 2 times 2. If we keep it in this form, this is called expanded form. I hope the name is self-evident. It's expanded. 2 times 2 times 2 times 2. That's the expanded form. If I write it this way, because there are 4 2's, 1, 2, 3, 4, this is called the exponential form. And again, I hope the name is self-evident, right? It's exponential because you're writing it with an exponent. This is expanded because it's written expanded. All right. The number 16 is called the standard form or the natural form. 16, that's its standard form or its natural form. So you have the standard natural form, you have the expanded form, 2 times 2 times 2 times 2, and then you have the exponential form, 2 to the 4th. All right. I'm saying all this right now at the beginning because for the next 45 minutes or so, that's all you're going to hear me say. Right? Let's take the composite number. This is also a composite number. 16 is composite. In other words, it's not a prime number. And then finally, I just have to say it. All of the numbers in the factorization are primes. The exponent is not required to be prime. All right, so you could definitely have non-prime exponents. I mean, we can't insist on that. That'd be asking too much. All right, so what we're going to start off with is some examples of exponentials and standard and expanded form. So evaluate 5 to the 3rd power. Let's do several of these. Let's do several of these. All right, so 5 to the 3rd power. So that would be 5 times 5 times 5. Okay. So that would be 5 times 5 is 25. And then 25 times 5 is 125. You could probably jump right to here if you like. If you can just go 5 times 5 times 5 and jump to 125, that's great. I am slightly breaking my own rule of moving sideways. I think you can allow me a little bit of freedom on that one because if I start moving this way, I'm going to butt into some other problems. So 3 times 3 times 3. Plus, I'm not really solving an equation. If I was solving an equation, I definitely would not be moving this way. I'm basically practicing my exponentials here. So I've got 3 times 3 times 3 times 3. If you're good at jumping, you already know the answer. It's 81. Yeah. Or you can do them in pairs. 3 times 3 is 9. The other 3 times 3 is another 9. I always recommend doing 2 at a time if possible. I mean, unless you have an odd number, then you obviously can't do that. And then 9 times 9 is 81. Another way to do it would be 3 times 3 times 3 is 27, and then 81 as well. But either way, you're going to get 81. All right, this is one of my favorite ones. 2 times 2 times 2 times 2 times 2. If you're good at jumping, you already know the answer. It's 32. Yeah. All right, or you can write it out. 2 times 2 times 2 times 2 times 2. Yeah, let's do them in pairs. 2 times 2. Here, I'll do a trio. So 2 times 2 is 4. And then 2 times 2 times 2 is 8. So boom, I got 32. This one has lots of different paths to get to 32, but no matter how you group it together, you're always going to get 32. That's the neat thing about these prime factorizations. Notice that all of these bases are prime. Yeah. So we call these the base. Yeah, all the bases are prime. The exponents aren't necessarily prime. Sometimes they are, sometimes they're not, just whatever they happen to be. Okay. What else can we do before we start getting into the deep end of the pool? We can evaluate. Let's just do one part on this one. 2 to the third times 5 times 7. Let's make it a little harder. Let's make it 2 to the third times 5 squared times 7. Just a little bit harder before we get started. Okay, so why am I doing it this way? This is what a prime factorization would look like when it's done. All right, so this is an example of kind of unfactoring and taking it from the exponential form. So this is a prime factorization in exponential form. I'm just going to say exp form. Then I'm going to write it out in expanded form. So 2 to the third means 2 times 2 times 2, and then 5 squared means 5 times 5. By the way, that's why I changed my mind at the last second. And then times just 1/7. So technically, there's an invisible 1 right here, but I'm not going to write it. So this is a prime factorization. These are both considered prime factorizations in expanded form. Oh, man, I have to write out the whole word now. So this is exponential. Now I have to say it because they both start with EXP. Oh, God, that could be confusing, huh? If somebody said EXP form, and then later on they say EXP form. Oh, God, there's 2 different EXP forms. Exponential and expanded form. All right. And then finally, I want my answer is standard form or natural form. So you can do this any way you like. You can go right to left. You can go left to right. You can group them in pairs. You can group them in trios. You can do whatever you like. I'll do a trio because I memorized 2 times 2 times 2 is 8. I would just memorize that. That's going to happen a lot in this class, so you might as well memorize it. 5 times 5 is 25, and then the 7 is just going to be the last thing we do. 8 times 25 is 200. How did I know that so fast? I don't even have my calculator out, right? It's because 4 times 25 is 100. So if 4 times 25 is 100, which everybody memorizes that, then 8 times 25 is 200. And then 200 times 7 is 1,400. All right, if I get too cocky, I might make a mistake. I know I've made mistakes in the past. Your job is to find my mistakes before I fix them, by the way. Whatever. So 1400. 1400 is the standard or the natural form. Okay. All right, enough playing around. Let's go ahead and do it. So those first few examples were just kind of to get you into the vocabulary, the terminology. I want you to know what I'm asking. If I just say prime factorization, typically what I'm wanting is the exponential form. That's typically what we want. Occasionally these things are the same, or there might be a problem that doesn't care either way. But typically this is typically what we're asking for in most of the questions. If I don't specify, then I don't care. That means give it to me anyway. As long as it's correct, I'll take it. All right, so find the prime factorization of 66. All right, so there are two methods. One is called the tree. The other one's called the ladder. It really doesn't matter. Sometimes I'll use a tree, sometimes I'll use a ladder. Right now I'm going to show you both. Okay, so for the tree. The tree, you make branches, and you can start with any factor that you can think of. Don't try to go straight to prime numbers. I mean, unless it happens to be that they're already both prime, something like 15 or something. Well, it would be 3 and 5, you'd be done, right? So I'm not going to give you that small of a number right now. So 66, just take the first thing you can think of. Most people think of 6 and 11. Yeah, remember, multiples of 11, although I didn't make a big deal about them, those are the ones that duplicate. 66, 44, 55, things like that. So 6 times 11. 11's already prime. All right, if it's prime, circle it. Okay. If it's not prime, don't circle it. All right, do not circle it. That's not prime. All right, prime factorization. All right, so now 6. Make another branch. Yeah, always do 2 at a time. Occasionally you can do 3 if it's one that you've memorized, right? Like 8, right? 8, you can do 3 branches, 2, 2, 2, and we'll get to that in a minute. So 6 is 2 times 3. Those are primes. And so the prime factorization is 66 is 2 times 3 times 11. Normally we put them in order. So that's how you do it with the tree. I don't think you'll be writing the 66. That'll already be there, or the question will be there like that. So I'm just telling you that this is an equivalent. If you want to check your answer, you better get 66. Check. Okay. All right. The other method is the ladder. The ladder, you start with the number, whatever you're doing, okay, and then you guess what's the smallest number. So you have to start with the smallest number. That's the problem with the ladder. If you don't start with the smallest number, it'll screw everything up. What is the smallest number that goes into 66? 2. Yeah, 2 is the smallest number. All right. Now 2 goes into 66. How many times? Well, 3. Yeah. 3 times 2 is 6. And then it goes another 3. 3 times 2 is 6. Remainder 0. Yeah. And so that's your first prime number. Then you do it again. Take the 33 and put it inside and do it again. What's the smallest number that goes into 33? Not 2. 2 doesn't work. 3 works. Okay. 3 goes into 33 11 times. 1 times 3 is 3. 1 times 3 is 3. Subtract remainder 0. Stop when this number is prime. Yeah, it's called the quotient. So if this quotient is prime, stop. Otherwise, keep going. All right, otherwise keep going. So in other words, if 11 was not prime, then I would do exactly what I did with the 33. I'd bring it down, it would become the next divisor, and I would do it all over again, okay? I probably shouldn't have circled the 33 because that's not prime. So you can use some other symbol besides a circle. So you only want to circle the primes, and so you get 66 is 2 times 3 times 11. It's exactly the same answer. This one doesn't have an exponential form because there are no exponents. So this is an example where the exponential form and the expanded form are the same. Yeah. So actually, I shouldn't say it doesn't have an exponential form. It does. It's just you can't see any of the exponents because all the exponents are 1. So technically, that's still exponential form. It's just the exponents happen to be 1. So, all right, want to try another one? I'm sure that's all you're looking forward to today, right? You didn't have any other plans today. Find the prime factorization in exponential form. Or sometimes I'll say use exponents. That's just to be absolutely clear. I'm like, all right, I'm just going to say use exponents, you know. All right. Oh, I got to give you a number. 80. Okay. All right, I like the tree personally. The tree has its issues, but the ladder one does too. I will do another one with the ladder eventually, just so you can see. The ladder works good for bigger numbers, maybe, where you get a lot of branches. Let's see. So let's do 8. We got, what do you think of 8 and 10? It really doesn't matter. No matter what you start with, you're all going to end up with the same prime numbers in the end. Some people might think of 4 and 20 or something. You could go that way too. So 8 is one of those exceptions where I kind of think a 3 branch is okay. All right, but there aren't very many 3 branches. You know, I think 8 is like that. 27 is like that. Yeah, you can do 3, 3, 3, but that's really about it. You're not going to get any more than that. Most of the numbers you're going to do with 2 branches, and then 2 and 5. And so those are all your. You don't really have to circle them, but I recommend circling them because those are your prime numbers. 80 is 2 times 2 times 2 times 2 times 5. Yeah, and then that's 4 2s. So we're using exponents, 2 to the 4th power, and then times 5. And that would be your answer. The ladder method is a pain in the butt for this one. It would take up a huge space. You know, you go 80 divided by 2. Actually, let's do it. 80 goes into 2 40 times. 42 goes into 40 20 times. 2 goes into 20 10 times. 2 goes into 10 5 times. Stop when they're all prime. 2 times 2 times 2 times 2 times 5. 2 to the 4th times 5. Same exact result. Yeah. Notice I used upside down division signs. Yeah. So there's that. Okay, example 6. They're going to get a little bit bigger. The upside down division sign just saves you from having to rewrite the previous quotient as a divisor again. If you do it upside down, it's already in the form of the divisor. I'll do that again maybe to show you another one. Prime factorization of 154. So let's try the tree method. 2, that's divisible by 2. By the way, if you're doing the ladder, that's just like the first cut in the ladder. 2 goes into 154. How many times? 100, 50. 100 divided by 2 is 50. 50 divided by 2 is 75. 100 divided by 2 is 50. 50 divided by 2 is 25, so we're up to 75. And then 4 divided by 2 is 2, so 77. Yeah. And then 77 is 7 times 11. And this is why I like the tree method, just because it's clean, you know, like that. And so you have 154 is 2 times 7 times 11. How about one more? Here's a really gnarly one, 360. All right, 360. Let's do the ladder method one more time. So 360, what's the smallest number that goes into 360? 2. Yeah. 2 goes into 360 180 times. All right, what's the smallest number that goes into 180? 2 again. Yeah. 2 goes into 180 90 times. Smallest number that goes into 90? 2 again. Yeah. 2 goes into 90 45 times. Now you got to be careful. The smallest number that goes into 45. 5. No. 3. See, I almost blew it. You know what, though? If you do a 5, you won't get the wrong answer. It just won't be in the nice order. So it's not really that big of a deal. Doing the smallest number is just a way of guaranteeing that you only get prime numbers here. So you wouldn't want to do 9 or 15 or any other number other than 3 or 5. So 3 goes into 45 15 times. What's the smallest number that goes into 15? 3 again. 3 goes into 15 5 times. Remember, you really shouldn't have any remainders. You should always get remainder 0, which is another reason why we do the upside down division. Upside down division doesn't really work very well if you have remainders, because there's nowhere to put the remainder. You're kind of synthetically dividing here. It's an artificial division. And then you have all of the prime numbers, and then you have 2 to the 3rd power. Yeah, because there's 3 2s. That's why this method, maybe I shouldn't have been so harsh on it. It's actually kind of neat. 2 3s, so 3 to the 2nd, and then 1 5. And there you go. There's the ladder. So trees and ladders. Next, we're going to talk about something a little bit different. So prime factorization is certainly not going away, but hopefully now you've had a nice exposition on how it works, and you can practice it on your own, and then we'll be working on it probably for the rest of the semester. It's one of those things that just keeps coming back. You least expect it. Oh, there's prime factorization again. All right. What are we up to? 7? Or was that just 7? I don't know. I lost count. So maybe that was 7. 6 and 7. Was that 8? So we're up to 8 now. Example 8. Something's telling me we're on example 8 now. Least common multiple. Least common multiple is abbreviated LCM for obvious reasons. Okay, so find the least common multiple. And we'll start with 2 numbers. Four and 15. Okay, so what is the least common multiple? There's a couple ways to think about it, all right? First thing I want to mention is the word least is a little bit misleading. I mean, because it does mean the smallest, so what it means is the smallest multiple of both 4 and 15. That's the common part. So it's the least multiple that's common. Yeah. The problem is it's usually not a small number. And so the word least or the word small sometimes poisons the mind. And I'll give you a problem and you'll think of a small number. Your brain immediately goes to small, right? So you should actually be thinking of a big number. At least as big as the biggest of the givens numbers. So I just want to say that right away. Before I do a single problem, I say, what's the least common multiple of 4 and 15? All right. No matter what happens in your thought process, no matter what kind of calculation you start to do, and some people will do it mentally. I'm going to show you sort of a combination of mental and written math. But you better get a number that's at least as big as the biggest of the two numbers. In other words, there is no way it's ever going to happen that the least will ever be smaller than the bigger one that you were given the two of. So we have 4 and 15. There's no way it's going to be smaller than 15. All right. It must be greater than or equal to 15. I just want to say that right away. Okay, so now here's the method. I like to do a vertical method. In other words, I take the numbers and I stack them on top of each other like this. And then I factor them. Use prime numbers. 3 times 5, 2 times 2. Okay? And then make these both the same. All right? Make them both the same. That's the key. All right? Make both of these numbers common. Make them the same. So, in other words, do whatever you got to do, right? Whatever you do to one side, do it to the other side. So let's just look at the top number first, right? Top number is 15, right? Notice what it doesn't have. It doesn't have any 2's. So let's give it 2 2's. Right. So you got to keep it equal. Yeah? And then now this side has 2 2's, but it doesn't have the 3, so give it a 3. And it also doesn't have the 5. And you have absolute power. You are an absolute tyrant here. You can give it whatever you want to give it, right? Whatever. But whatever you do to one, you got to do to the other. All right? Once all of these equal the same thing, you know that you're done. All right? In other words, all of these are the same thing. Look, and this is really fun mental math practice. This is where the combination of written and mental math come in handy. All right, now evaluate these. So evaluate them. Now I know eventually you probably get lazy. So the top right, what do we got? 3 times 5 is 15. 15 times 2 is 30. 30 times 2 is 60. So that's 60 right there. All right. How about over here? 2 times 2, that's 4. 4 times 15, that's also 60. Yeah. They're all going to be 60. 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 60. Yeah. Yeah. 5 times 3 is 15. 15 times 4 is still 60. Yeah. So the LCM is 60. Now, of course, this is my really exaggerated demonstration. You don't really have to multiply all of them out. All right? They should all be the same. So in other words, once you've done one of them, they're all going to be the same. I mean, unless you made a mistake. I guess doing all 4 of them checks that you didn't make a mistake. They better all come out to be the same. All right? Now, by the way, some of you are sitting there watching the video right now going, Dr. Jordan, why didn't you just multiply 4 times 15? Right? Well, why didn't I? Because that's not always true. And if I would have just multiplied 4 times 15, then you would think, well, you just always just multiply the two numbers together. And I don't want you to think that. So let's do another example. Find the LCM of 18 and 15. If you just multiply these two numbers together, you're going to be in real trouble. All right? It's just not going to work. You're going to get such a big number, it's going to be way too big. All right. Now here's the thing I want to make sure about. All right. There are two numbers, right? 3, yeah, goes into both of these. Yeah, 18 divided by 3 is 6, and 18 divided by 15, 15 divided by 3 is 5, yeah. So, some people, LCM is 3, yeah. Some people say that, they do. And I understand why. You know, I'm not disconnected from reality here. I understand why. It's because the brain thinks least. Yeah, that's just the way the brain works. I mean, I have a brain, right? You see a problem, least, and you go, oh, okay, 3, right? 3 goes into 18, and 3 goes into 15, but that is absolutely not true. No way, don't do it, don't do it. Remember, the answer will be at least 18 because 18 is the bigger of these two numbers. So really the word least kind of throws your brain in the wrong direction, right? The word least means it's going to be at least 18. It's actually going to be bigger than 18, but if you get an answer that's smaller than 18, then you are misreading the terminology, okay? So I'm going to do my stacking method. 18 is 9 times 2. I want to use only prime numbers, so I'm going to do 3 times 3 times 2. So make sure you're using all primes. Okay. So don't stop until you get all primes. 15 now. Let's do 15. I think we get that right away. 3 times 5. Remember, never use 1. Otherwise, you just have a bunch of useless 1s out here. Okay, and then remember the rule. So we're not looking at this one. We're not looking at 9 times 2. We're looking at this one. I know there's people that say I'm crazy and say you don't have to use all primes. You can still get the right answer. But no, yeah, sure, yeah, and so what? But do it with all primes, and you'll be 100 times more likely to be successful. Okay, so it's all about planting that. How do I really want to do this? All right, so remember what we did in the last one? You can give them anything you want to give. You are the supreme tyrant, or the supreme benevolent fascist. You can do whatever you want. And it doesn't matter what order they're in. I don't care. You don't have to squeeze them in the right order here. So this one has 2 3s. This one only has 1 3. Our goal is to make them common so that they're happy. So put a 3 there, put a 3 there. All right. Oh, this one doesn't have a 5. Oh, that's okay. Give it a 5. You can do it in any order you like. Put a 5 there, put a 5 there. Now everybody's happy, right? Somebody's going, I'm not happy. I'm not common, right? I'm missing something here. What's this one missing? It's missing a 2. I'll give them a 2. There you go. All right. And then just pick one of these. Doesn't really matter. Pick one and multiply it. Once they're all happy, make sure they're all the same, right? 2 3s, 2 3s, yeah. A 2, a 5, a 5. Everybody's happy. So pick one and multiply. 5 times 18, that's 90. And so that's your LCM. LCM is 90. If you want to check, it's not that bad, right? Let's try this one. 2 times 3 is 6. 6 times 15, still 90. Yeah. 3 times 5 is 15. 15 times 3 is 45. 45 times 2, still 90. Yeah. If they don't all come out to be 90, I know I made a mistake here. How about this one? 3 times 3 is 9. 2 times 5 is 10. 9 times 10 is still 90. Okay, so that's how you find the LCM. Once you can find the LCM with 2 numbers, then we'll move on to finding the LCM with 3 numbers. All right, let's cut to the chase now. Okay, let's just do it. We got a lot of work to do. Take the biggest number first. You know your answer has to be at least that big. Sometimes that is the answer. You know, sometimes that's just the way it works out. If this number is already a multiple of these 2 numbers, you guys might want to check while I'm talking. You might get ahead here. All right, so let's go ahead and do this. Let's do the ladder method. So 2, you know, it's funny, I started this lecture, I didn't really like the ladder method. I particularly like the tree method, but by the end of it, I think I like the ladder. 216 divided by 2, 108 divided by 2, that's 54. Divided by 2 again is 27. Divided by 3 is 9. Divided by 3 is 3. So 1, 2, 3, 1, 2, 3, 4. So I got 2 to the 4th and 3 to the 3rd. All right. Should we do, I guess 96 next? 96 divided by 2 is 48, divided by 2 is 24, divided by 2 is 12, divided by 2 is 6, divided by 2 is 3. So that's 1, 2, 3, 4, 5, 2 to the 5th, and a 3. And just to keep the tree alive, I got 1 tree here in the middle. 36 is 6 times 6, 6 is 2 times 3, and 6 is 2 times 3. So 36 is 2 squared and 3 squared. Just because I do still like trees. All right, so now we got all their prime factorizations. I guess one of the reasons why I don't like the ladder is because it takes up all my space. So let's see. Just give it one last look. Take a peek at it or something. I don't know. I need the space. Here, this is the oldest. Let's take the oldest space first. All right, so we've got 432 is 2 to the 4th. And 3 to the 3rd. We got 96 is 2 to the 5th and 3. And then we've got 36 is 2 to the 2nd and 3 squared. All right. And now our goal is to make them all the same. All right, they all want to be the same. If you already know the answer, just give them all what they need right now, and you can spare all this extra talk. Okay. The most number of 2's is 5, so this one needs 3 more 2's. And now it has 5 2's. 2 times 2 times 2. This one already has 4, so it only needs 1 more 2. Oh, and I better balance everything out over here just to not break the law of equality, okay? All right, and then let's go to the 3's. Let's see, who's got the most number of 3's? It's funny that you always compare the least with who has the most. Yeah, that's how you do it. Let's see. So this one needs 2 more 3s. So now altogether, this has 3 3s. And this one already has 2, so it only needs 1 more 3. And I should be very careful that I give it to everybody. There we go. And now just pick one, whichever one looks the easiest to you. I'm going to pick the easiest one. So pick the easy one. 4 times 2, 32 is 864. There you go. And if you really love checking, I know I do. Let's just do a couple of them. Let's do this one right here. All right. What would that one be? 3 squared is 9. 9 times 96. 9 times 6 is 54. Carry the 5. 9 times 9 is 81 plus 5 is 86. It's the same thing. Doesn't matter which one you pick. They're all going to be right. Yeah. Here, let's try this one. 2 squared is 4. 3 squared is 9. So that's 36. I like to cross them off as I go. 2 to the 3rd is 8. It's good for the brain. 8 times 3 is 24. Let's see. 24 times 36. Oh, man. 4 times 6 is 24. Carry the 2. 4 times 3 is 12 plus 2 is 14. Put a placeholder. Cross off your old ones. 2 times 6 is 12. Carry the 1. 2 times 3 is 6 plus 1 is 7. Sometimes I get these wrong, by the way. You can use your calculator if you really want. 4 plus 2 is 6, and 7 plus 1 is 8. Woo-hoo! I'm not doing it anymore. Until we meet again some sunny day, I'll see you on the internet.